9.1 is a review from Algebra 1 looking at Pythagorean theorem. So most of you, if you remember anything from Algebra 1, probably remember a squared plus b squared equal to c squared. Maybe not how to use it, but you at least remember learning it. So that's what we're starting with in Chapter 9 is right triangles, finding the length of a missing side in a right triangle specifically. So Pythagorean theorem is a squared plus b squared equal to c squared, where a, b, and c are corresponding sides on a triangle. C is always the hypotenuse or the longest side on the triangle, and the hypotenuse, in case it's not clear which side is the longest, especially if you're trying to find it, is always across or opposite from a right angle. So if I were to draw a triangle here, well, maybe I should draw it well. There we go. So drawing a right triangle here, give it a right angle. The side that would be the hypotenuse. If I use this right angle area as a starting place and I draw an arrow from it to the side opposite, we would say that that's the hypotenuse. So here's my hypotenuse. My stylus is not writing very well today, sorry. And your hypotenuse is always C in Pythagorean theorem. And then the other two, which you've heard these words before as well, they're just called the legs. And the legs are either A or B. You can choose which side you want to be which. So these are legs. They're not always congruent to each other, so don't think of it that way. They're just either A or B. So whatever value that side is, whether it's the missing side or a side that's given to you, you'll just plug in either of those sides for A or B, and then the hypotenuse, again, that value, whether it's missing or given, will always be C. We also have something called a Pythagorean triple, and that's just a set of 3 positive integers that satisfy the equation. So meaning if you found a missing side and you have all 3, A, B, and C, if this is true, then it forms a Pythagorean triple. Most common Pythagorean triples are in bold. You'll see them pretty often. And that's a 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25, where the last number, the largest number, is the hypotenuse. And these are not the only ones. They're just, again, the most common. So if you get a whole number using Pythagorean theorem and you plug into this equation, then they satisfy a Pythagorean triple, even if they're not on this list of bold, common Pythagorean triples. So let's look at example 1. Determine whether the Pythagorean theorem can be used. And I said this at the beginning, but the only way Pythagorean theorem can be used is if the triangle is actually a right triangle. And in this case, in both example 1 and example 2, that's the first part of the question, determine whether it can be used. It can be. I see the right angle in the triangle. It's marked, so that means I can use Pythagorean theorem here, which is nice. It's pretty simple to plug into, get you some calculator work. So yes, it can be used for yes. If it can, find the value of x. So the most important part, again, is determining whether or not, or which side is C. So it's the side across from the right angle. Always. It's always the longest side. And in this one, it's clear that the missing side is our longest side. So that's fine as well, but for some more shorter triangles or ones that seem to have more even sides in length, then this is important to know. So we've got 5 squared as one of our sides. 5 squared is A or B. or 5 is a or b, and then you want to square it, then 12 is whichever one 5 wasn't. And then c squared is x squared, the piece that we're finding, x squared. So then we just want to solve this. You'll have to pull out your algebra skills. You can just plug this whole piece into your calculator. So that's 25 plus 144. So 169. So we want to know what just x is, and hopefully you remember this, but to get rid of this squared on the x, the exponent, I have to undo it by its opposite operation. Just like if you want to get rid of division, you multiply. If you want to get rid of addition, you subtract. So the opposite operation of squaring something is a square root. So I want to take the square root of both sides. When I do that, again, it's an opposite operation, so opposites cancel each other out, and I'm just left with the x value over here on the right, and then whatever the square root of 169 is. In this case, it's a perfect square, so you're going to get a whole number out. It's 13. Okay, so x, this side is 13. Okay, and when you look over here at your chart, a 5, 12, 13 is actually a very common Pythagorean triple. So, if we had noticed that, we could have saved ourselves some work, but it's important to practice. So same idea with example 2, we just want to plug those things in. Again, the c is the most important variable that we're plugging in as far as a squared, b squared, and c squared goes. So again, opposite of the right angle. This time, it's not the x value that we're finding. The x value is either a or b, whichever you would like it to be. So 14 is my c value. So I'm going to have 7 squared plus x squared. You could have written them in a different order, as long as 14 squared is your c squared value. All right, so work that down. Okay, so pulling out those algebra skills, we want to solve for x here, and the next step would be to get this 49 to the other side, so the x is by itself. So we're going to subtract 49 from both sides. We've got x squared equal to square root of 147. Okay, so that gives us, oh, sorry, square root. Why did I do that? The square root is after. I shouldn't have done that. So x squared is equal to 147. To solve, we want to take the square root of both sides. So square root both sides, those cancel. Okay, so x is just square root of 147. And if we look at this chart to see if it's a Pythagorean triple, one of the most important parts of it is that it says it's a set of 3 positive integers, and an integer is a whole number. And so square root of 147, you can take that, but it gives you a decimal. It's about 12.12. We don't want decimals, but this is not a whole number. It's not an integer that's positive. So this would not be a Pythagorean triple. Look at example 3. So example 3 is talking about the converse of the Pythagorean theorem. So remember back to your if-then days when we were looking at conditional statements, converse, inverse, contrapositive. It says if the square of the length of the longest side of a triangle is equal to the sum of the squares of the legs, then the triangle is a right triangle. Essentially, if a squared plus b squared equals c squared, then we know that there's a right angle in the triangle. And that probably sounds very similar to what we've been doing, because it is, except for if you look at examples 1 and 2, or even the stuff from this page, we already knew there was a right angle in the triangle, and we were finding a missing side. And we could use Pythagorean theorem because we knew there was a right angle. It was marked. And we could find that missing side. But with this one, we don't see a right angle and there are no missing sides. So we're still wanting to use that a squared plus b squared equal to c squared. What we're wanting to see is if that's true. And if that doesn't make sense, it should in a minute. We're wanting to see if the left side of the equal sign is the same as the right. So we want to find c, that's the most important letter, c. So we have a squared plus b squared equal to c squared. And C is, again, the longest side or the side opposite of the right angle. We don't see a right angle, so we want to see which side is the longest. And I said we don't use decimals. We're not using them to find any value, but we do want to get an approximation of what square root of 113 is. So if you put square root of 113 in your calculator, you're going to get a decimal. Okay, it's about 10.6. And the reason we do that is we just want an approximation of which side is largest. Square root of 113 side does seem to be the longest, but we can't go off of assumptions. Things are not always drawn to scale. So 10.6 is our longest side. So what we want to do is we want to say that square root of 113 is our C value. So making sure I use parentheses so we make sure that this exponent is evenly distributed. Some of you don't like parentheses, I'm sorry, they are important. So we have 8 squared plus 7 squared, and that just comes from the other two sides. Doesn't matter which one is which, you could have written 7 squared plus 8 squared. So we have 64 plus 49, if we simplify that. And then again, we have an exponent and a square root. Those cancel each other out, so this side is 113. Okay, so we just want to combine 64 and 49, and we also get 113 when we combine those. So we have 113 equals 113. And that's true. That means that this was a right triangle. So that means even though it's not drawn here, we know that there's actually a right angle here. Okay? This a squared plus b squared equals c squared is true. Let's say we had gotten like 105 equal to 113. That's not true. 105 does not equal 113. So if those were the values that we had gotten, we would know that the triangle that we started off with, whatever gave us 105, was not actually a right triangle. That's all that means. So that would be what we were looking for. So actually looking right underneath it, leading into what I had just said, is the inequalities theorem, Pythagorean inequalities theorem. Meaning if a squared plus b squared is larger, so you don't get that the left is equal to the right like we did. You don't get 113 equal to 113. If a squared plus b squared was the larger side, and I'm going to write that right here because it is printed, but it's written backwards from what you're used to seeing, and I don't want any confusion. So if a squared plus b squared is greater than c squared, then whatever kind of triangle it is, it's an acute triangle. It didn't have a right angle. It had an acute angle across from the hypotenuse. And then the opposite, if a squared plus b squared is not greater than c squared is the biggest side, that means that it was an obtuse angle right here. See, across from the hypotenuse. So let's look at example 4, and that might make more sense. So we say the lengths of the side of a triangle are 4.3 feet, 5.2 feet, and 6.1 feet. So we don't need to know what it looks like. We have their measurements. Is the triangle acute, obtuse, or right? So we want to use a squared plus b squared equal to c squared here. And we want to see if it's true. So again, the most important part to know is C. Here's C. It's the largest side. It's bigger than 5.2 and 4.3, so I know it's the biggest side. So I want to plug these things in. So I have 6.1 squared, 5.2 squared, and 4.3 squared. Okay, so there's that. I just want to work those things out. So if I square both of these, or all three of these things, I have 18.49 plus 27.04. And 6.1 squared is 37.21. So I want to add these two things, and that gives me 45.53. And that is not equal to 37.21, right? Those are not the same value on the left and the right. And so what we see here, since they're not the same, is that the right side, a squared plus b squared, is larger. So if I look up here, I see that a squared plus b squared greater than c squared is right here. That's what I have. So that means that this is an acute triangle, whatever it looked like.